Okay, we're going to continue this example that we started in class. And what we want to do is find the solution to the initial value problem, y double prime plus 2y prime plus 2y equals f of t, where f of t is this discontinuous function. Let's sketch f of t really quick here. So f of t looks like, this is t here, oops. This is t. It's 0 when t is between 0 and pi. When we get to 2 pi, or when we get to pi, f of t jumps up to the value 1 between pi and 2 pi, and then is 0 afterwards. So it's this step function, this some combination of Heaviside functions. And we saw in lecture that we can actually write f of t as the Heaviside function, which is 1 at pi and 0 beforehand, u sub pi minus u sub 2 pi. That would give us this function f here. Now to solve this initial value problem with our initial conditions here, y of 0 is 0 and y prime of 0 is 1, we're going to take the Laplace transform of this entire function here, or this entire equation, I should say. Now remember that our other techniques for solving these types of problems sort of doesn't fit the inhomogeneous term here, because this is a discontinuous homogeneous term and it doesn't really fit the forms that we've had in the past. So that's why we're going to consider the Laplace transform. So taking the Laplace transform, take the Laplace transform of the ODE. Well, the Laplace transform of the second derivative will give us s squared times the Laplace transform of y minus s times y of 0. Actually, maybe I'll write this as capital Y of s because it's a function of s, minus s times y at 0 minus y prime of 0. This whole thing here is the Laplace transform of y double prime. Now we want to add 2 times the Laplace transform of y prime. That's going to be 2 times s y of s minus y at 0. So this is plus 2 times the Laplace transform of y prime plus 2 times the Laplace transform of y. Okay, that is equal to, maybe I'll move this over for a second. That is equal to the Laplace transform of the right-hand side. Now, earlier, we wrote the right-hand side function f as some combination of Heaviside functions, and we can take the Laplace transform of this. We computed it in class. This will give us e to the minus pi s minus e to the negative 2 pi s all over s. This is the Laplace transform of f. Okay, so we've just taken the Laplace transform of our whole equation. Now we can substitute our initial conditions where we have them here in our equation. So y of 0 is 0, y prime of 0 is 1, and y of 0 is 0. So let's go ahead and substitute those in. I have s squared times capital Y minus 0 minus 1 plus 2s capital Y minus 0 plus 2 times capital Y. That is still equal to our right-hand side here. Just copying that down. And now I want to solve for capital Y. So I need to group things that have capital Y in them. That gives me s squared plus 2s plus 2 times capital Y minus 1, and that's equal to our right-hand side. I'll move this down so that it's not too crowded. I can add this 1 to both sides. So really I have plus 1 there, just added that over. And now I'm going to divide both sides by s squared plus 2s. So I'm trying to isolate this capital Y. So I'm going to go ahead and divide this over. So really I end up with y of s is 1 over s squared plus 2s plus 2 plus e to the minus pi s minus e to the negative 2 pi s all over s times s squared plus 2s plus 2. And that's coming from just dividing by this factor. So where are we going with this? Well, capital Y, so recall that capital Y is the Laplace transform of our solution, little y here, little y of t. So if I want to figure out what the heck little y of t is, I need to take the inverse Laplace transform of capital Y. So then y of t is the inverse Laplace transform of capital Y. Well, capital Y is this expression, so I'm going to go ahead and write that. Inverse Laplace transform of 1 over s squared plus 2s plus 2 plus the inverse Laplace transform of e to the negative pi s minus e to the negative 2 pi s all over s times s squared plus 2s plus 2. So now I'm going to focus on computing the inverse Laplace transform of these expressions here. I'm going to go ahead and focus on these sort of one at a time. I'm going to call this expression term 1 and this expression term 2. And I'm going to compute these separately and sort of kind of just keep track of things. So just remember at the end, y of t is going to be term 1 plus term 2. So let's think about term 1. We have this s squared plus 2s plus 2 in the denominator. That doesn't really match anything in our Laplace transforms table. So instead, and we can't factor this, so it seems like we're out of luck, but instead, let's think about completing the square. Let's complete the square. So s squared plus 2s plus 2. To complete the square, we need to add, so let's say this is equal to s squared plus 2s plus 2. We need to add actually 0, so plus 0, but 0 in a creative way that gives us something, that gives us some help. Now, usually when you have a polynomial, say x squared plus bx plus c, to complete the square, actually we could have ax squared plus bx plus c. To complete the square, you would add b over 2a squared and then subtract b over 2a squared. So notice that adding and subtracting the same thing is like adding 0, but this lets us do something kind of cool and have a square of something in our function. In this case, the equivalent of that would be adding our a is 1. Sorry, I should say our a is 1. Our b is 2. So if I were to add b over 2a squared, that's going to look like 2 over 2 squared minus 2 over 2 squared. So I'm adding 1 and I'm subtracting 1. S squared plus 2s plus 2 plus 1 minus 1. So I've added 0 in sort of a nice way. Okay, well, what does that help us with? I'm going to utilize this positive 1 here. I'm going to put that next to my terms with s. So I have s squared plus 2s plus 1. These other two terms, I have 2 minus 1. That's what I have left over. That is 2 minus 1, that's 1. So I have plus 1. Now, this expression here is something that I can factor. I can factor this. Really, I can write this. This part here is s plus 1 squared, and then I just have this like plus 1 left over. This is s plus 1 squared plus 1. I have completed the square. Now remember that this was the denominator of term 1. So going back to term 1, I'm looking at the inverse Laplace transform of 1 over s squared plus 2s plus 2. Well, if I complete the square of the denominator, that's inverse Laplace transform of 1 over s plus 1 squared plus 1. this expression does look like something in our Laplace transform table. If you look at your Laplace transform table, you'll see something that looks like b over s minus a squared plus b. In this case, a is -1, because I have the +1 here, and b is 1. And the expression that corresponds to this Laplace transform, or in other case, the inverse Laplace transform of this, is e to the at sine of bt. So really, the inverse Laplace transform here is e to the -t sine of t. And that's it for term 1. We still need to handle term 2, but so far we have the inverse Laplace transform of this first term. All right, let's move on to term 2. Term 2. Really, we want to find the inverse Laplace transform of e to the -pi s minus e to the -2 pi s all over s times s squared plus 2s plus 2. All right. Let's give this expression a name. Instead of thinking about the inverse Laplace transform just yet, I'm going to call this h of s, and we're trying to find the inverse Laplace transform of h of s. Well, let's focus on just a portion of this term. Remember that these factors of e to the minus something s, that's telling us that a heaviside function is going to come up at some point, but we also need to think about the things that don't involve these expressions. So you could split this up to think about it. Actually, I'm not going to split it up yet. Let's just think about this portion of the expression. So let's consider 1 over s times s squared plus 2s plus 2. That is the portion of this expression that does not involve these exponentials. Now this is factored, right? The denominator has 2 factors. So we'll need to split this up using partial fractions. This is equal to a over s plus bs plus c over s squared plus 2s plus 2. Now we're trying to split up this in partial fractions. Now if we get common denominators, this tells us that 1 is equal to a times s squared plus 2s plus 2 plus b times s plus c times s. Okay. Well, if I plug in s equals 0, that would knock out this term, right? That would get rid of that. And if I plug in, I would get 0 plus 0 plus 2. So I'd have 1 is equal to 2a, or in other words, a is equal to 1/2. It's not super obvious what to plug in next. So instead, let's just focus on setting a equal to 1/2 and then equating coefficients. So we know that a is 1/2. So I can say 1 is equal to a is 1/2. So I'm going to just replace that there. 1/2 times s squared plus 2s plus 2. And I don't necessarily know what bs plus c is yet, or b or c are. But let's just do this sort of the quote unquote longer way. You'll see that it's actually not that long. We're just going to combine like terms in s and then equate coefficients on powers of s. So I have 1 is equal to, the terms that involve s squared are going to be b plus 1/2 times s squared, plus the terms that involve s are going to be c plus 1 times s. And then the constant terms are just going to be a 1. I need the powers of s, I need the coefficients on s squared on the left and the right to be equal to each other. Well, there are no coefficients on s squared on the left, so I need b plus 1/2 to equal 0. In other words, b is equal to -1/2. Similarly, there are c plus 1 coefficients on s on the right, but no coefficients on s on the left. So c plus 1 equals 0. c equals -1. And then 1 equals 1, so that's, good sign my constants match. Okay, so I have A, B, and C. So let's write out what this looks like, what this expression looks like now with our values of A, B, and C. I'm actually going to make all of this smaller, otherwise I will run out of room. Yeah, I'd like to keep some of this on the same slide. Okay, so far we have 1 over s times s squared plus 2s plus 2. That is equal to a, which is a half over s, plus b is -1/2 s times s, and then c is -1 over s squared plus 2s plus 2. Now, this still, remember, we want to take an inverse Laplace transform here, but this still doesn't quite look like something that we can take an inverse Laplace transform of. So we need to do some more manipulation. One of these manipulations we already did. We already completed the square for this expression. So let's replace this denominator by our completed version. This term already looks like something like a Laplace transform. We know that the Laplace transform of 1 over s is 1, or the inverse Laplace transform, I'm sorry, of 1 over s is 1. So this term is fine, but this one's giving us a little trouble. So let's leave the first part alone, and we'll write out the completed, the version where we completed the square on the second term. So we said this was s plus 1 squared plus 1. Now I'm going to go ahead and factor out a 1/2 here. So I have a half over s plus, actually I'll factor out a -1/2 because that's what's in front of this term here. So -1/2 times, and what's left over in the numerator is s plus 2 all over s plus 1 squared plus 1. Again, this doesn't exactly look like something that we know the inverse Laplace transform of, but it's close, it's almost there. It's really this numerator that's sort of off at this point. But I can rewrite s plus 2 as s plus 1 plus 1 and then split things up, and that will look like something that we can take the inverse Laplace transform of using our table. So I have a half over s plus -1/2 times s plus 1 over s plus 1 squared plus 1. And now if I split this sum, this piece looks like something we can take the inverse Laplace transform of. And this piece also looks like something we know the inverse Laplace transform of. So let's write this as a half over s plus -1/2 times s plus 1 over s plus 1 squared plus 1 plus 1 over s plus 1 squared plus 1. And remember here, I'm just splitting up this fraction into this piece and this piece. Now, each of these terms is something that we have in our table. So what we really know is that the inverse Laplace transform of this expression, I'll go down here like this. If I say, let's say if I call this capital F of s, if I say that that is 1 over s times s squared plus 2s plus 2, then the inverse Laplace transform of capital F, remember this was just a piece, this was just a portion of the computation we wanted to do. But in any case, it's the inverse Laplace transform of really this expression. We just sort of manipulated things and we did partial fractions and sort of moved things around. So a half over s plus negative a half times s plus 1 over s plus 1 squared plus 1 over s plus 1 squared plus 1. Now, because the inverse Laplace transform is also a linear operator, we can sort of distribute over the addition and factor out the constants or the scalar multiples. So I have a half times the inverse Laplace transform of 1 over s plus negative a half times the inverse Laplace transform of s plus 1 over s plus 1 squared plus 1 plus negative a half times the inverse Laplace transform of 1 over s plus 1 squared plus 1. Now, if you look at your Laplace transform table, you'll see that this expression corresponds to the, this will give us the inverse Laplace transform of, will be e to the negative t cosine t. And this one we found earlier, this corresponds to e to the negative t sine t. And just remember that we have these factors of negative a half. This inverse Laplace transform corresponds to the function 1. So we have 1/2 times the function 1 plus, or really minus a half, so plus negative a half, e to the negative t cosine t minus a half times e to the negative t sine t. Okay. Now this wasn't the full term on the right-hand side, or this wasn't the full term 2 that we had underlined. The term in our ODE, the term in the differential equation was really, if I scroll back up, it was really e to the negative pi s minus e to the negative 2 pi s times this term that we just found inverse Laplace transform for. So really, it was e to the negative pi s minus e to the negative 2 pi s times our function that I called f of s. So this function here. That was the term that we had. So it was e to the negative pi s minus e to the negative 2 pi s all over s times s squared plus 2s plus 2. That's what we started with. Now I'm going to split this fraction up. I'll split it up into this piece and this piece. So I've got e to the negative pi s over s times s squared plus 2s plus 2 minus e to the negative 2 pi s over s times s squared plus 2s plus 2. So really, if I can move this over just a little bit, I have e to the negative pi s times that thing that I called capital F of s, that's what I defined it to be up here, minus e to the negative 2 pi s times f of s. That's what I actually want to take the inverse Laplace transform of. This up here is going to help us though. We know the inverse Laplace transform of capital F. And whenever we have these like e to some factor, some constant times s, that tells us that it's some sort of like Heaviside function. So some sort of Heaviside function is going to be involved. If you look at theorem, I believe it's 6.3.1 in your textbook, you have that the inverse Laplace transform of e to the minus cs times f of s is the Heaviside function u sub c of t times little f of t minus c, where little f is the inverse Laplace transform of capital F. Okay. So we're going to apply this reasoning to the expressions we have over here. It looks very similar to our expression. Okay. So in this case, let's let little f of t, actually, that's probably not great notation because I already used f earlier. I used f as our like right-hand side function. Let's let, I'll just use like little h. Let's let little h of t denote the inverse Laplace transform of that function we just took the inverse of. So s times s squared plus 2s plus 2. Say that's our inverse Laplace transform. Okay. Then if I want to compute the inverse Laplace transform of e to the minus pi s times that function, s squared 2s plus 2, if I go back up to my theorem here, I have e to the minus cs times some function of s. So that's going to give me the Heaviside function u pi of t, where the pi is coming from this term here, times the inverse Laplace transform of this function, but shifted by pi. So times h of t minus pi. Remember, I said little h was my inverse Laplace transform. Okay, well, that means I need to look at the inverse Laplace transform of h, and wherever I see a t, I'm going to write t minus pi. So this will be u sub pi of t times my inverse Laplace transform is right up here. So I'm going to use this function, and wherever I see a t, I'll write t minus pi. I'm actually going to copy and paste this. So earlier we had, we'll do this in purple. We have that h of t is the inverse Laplace transform of 1 over s times s squared plus 2s plus 2. And we already computed that. That's the whole inverse we took earlier. Now, h of t minus pi is this expression, but wherever I see a t, I'm going to write t minus pi. So we have 1 half minus a half e to the negative, and now I have a t there, so I'm going to write t minus pi in parentheses. Cosine of t, but I'm going to write t minus pi, minus a half e to the negative. Instead of t, I'm going to write t minus pi in parentheses, sine of t minus pi. Okay, and it turns out that cosine of t minus pi is equal to negative cosine of t, and sine of t minus pi is equal to negative sine of t. So really I can write this as u sub pi of t times a half plus a half e to the negative t minus pi times just cosine of t plus a half e to the negative t minus pi sine of t. Now, very similar idea. I can do the same thing similarly. The inverse Laplace transform of e to the negative 2 pi s times 1 over s times s squared plus 2s plus 2. It's going to be almost the same exact thing, except wherever there's a pi, instead of pi, I'll have 2 pi. So same thing, just instead of pi, I'll have 2 pi. So you can go ahead and check that this would give me u sub 2 pi t times a half minus a half e to the negative, and then in parentheses, t minus 2 pi cosine t minus 2 pi minus a half e to the negative t minus 2 pi times sine of t minus 2 pi. But because cosine and sine are 2 pi periodic, meaning they repeat themselves every scalar, every integer multiple of 2 pi, cosine of t minus 2 pi is the same as cosine, and sine of t minus 2 pi is the same as sine. So instead of writing all of that, I can replace cosine of t minus 2 pi with cosine. I can replace this with sine. So really, I've got u sub 2 pi of t times a half minus a half e to the negative t minus 2 pi times cosine of t minus a half e to the negative t minus 2 pi sine of t. Okay, we're almost there. This was all to get the inverse Laplace transform of term 2. Remember, all the way back up here, we're focusing at this moment on this term. We just need to add these pieces together. So what we have, if I scroll all the way back down, we had the inverse Laplace transform of what I called term 2. That is going to be the inverse Laplace transform of e to the negative pi s over s times s squared plus 2s plus 2 minus, the inverse Laplace transform of e to the negative 2 pi s over s times s squared plus 2s plus 2, which we already computed. We computed each of these things separately. So I have u pi t times a half plus a half e to the negative t minus pi cosine of t plus a half e to the negative t minus pi sine of t minus u sub 2 pi of t a half minus minus a half e to the negative t minus 2 pi cosine of t minus a half e to the negative t minus 2 pi sine t. And you can combine these in a slightly, more compact way, maybe. We can group some things together. I have a half times u pi of t minus u 2 pi. And then I have a half times u pi t e to the negative t minus pi. And all of that is times cosine t plus sine t plus a half u sub 2 pi of t e to the negative t minus 2 pi times cosine t plus sine t. We're almost done. Not quite, but almost there. Remember that our solution, this little y of t, was the inverse Laplace transform of this first part plus the second part. What I just wrote down was this piece. We still need to add this piece. Remember, we already computed term 1. So term 1 plus term 2. So I need to add e to the negative t sine t, and then I will have my solution. So let's go all the way back down. I'm just going to copy this. Okay. So I have y of t is e to the negative t sine t. That's what we had from the first part of our solution, plus, and then this whole expression that we just found, which I need to make smaller so that it fits on this line. There we go. This is our solution to the initial value problem. Now, if you go and plot this solution, maybe I should put a box around this so that it feels more final. So here's my solution to the initial value problem. Let's look at what the graphs of these functions look like. This is just a little bit of extra stuff here. So let's first look at what would happen if our function, our differential equation, had no forcing term. This is the solution to y double prime plus 2y prime plus 2y equals 0. So I've replaced, instead of that discontinuous function, I have no forcing here. Y of 0 is 0 and y prime of 0 is 1. That's what this function looks like. Now, what I want to compare this to is what happens when we do what we just did. We sort of add a forcing term. That forcing started at pi, which may be somewhere around here, and ends at 2 pi, which is maybe somewhere around here. So what happens in this region when we sort of flip a switch, turn on the switch and then turn it off? And if you plot the solution that we just found, you will get this expression, or this plot. So here I've plotted both the forcing function. Notice that it jumps up to 1 when t is pi, and then jumps back down to 0 when t is 2 pi. And what happens in our solution here is that it's sort of, this is like the homogeneous part. It looks like it should sort of go down to 0 at this point. But right here is where the switch turns on, and we immediately sort of shoot a kick into our system. At this point is where the switch turns off, and you can see that the homogeneous solution sort of takes over again, and we sort of repeat the behavior that would have happened if we had no forcing. So that's the end of this problem. I hope you found it helpful. Let me know if you have any questions.